Our next speaker is Minzer from MIT, and he'll tell us about the approximability of satisfiable CSPs.
Thank you very much for the introduction, and thank you for coming. So unfortunately, I couldn't make it because I was feeling a bit sick, but anyway, I hope to make it up to you by mentioning something that I hope you like, which is very recent, but it will only be on the last slide, so please don't fall asleep until then. So I'm going to talk about approximability of satisfiable CSPs and some related stuff, so let's get going. So the main topic of discussion today is going to be constraint satisfaction problems and their complexity. So what is a constraint satisfaction problem? Well, let's start with an example. So we all know and like the three-sat problem, but now I'm going to state it in a slightly weird way. So I'm going to say three-sat. Well, for that, I'm going to define a predicate, P. The predicate takes three Boolean values, X, Y, and Z as inputs, and as an output, 1 bit, which is the O of the bits. And once we have defined this predicate, the three-sat problem consists of, an instance of the three-sat problem consists of a collection of variables, x1 to xn, and a collection of constraints. And the constraints of the form P of some subset of variables or negations is equal to 1. And the goal is to determine whether a given instance is satisfiable or not. Meaning if you can find a Boolean assignment to the variable that satisfies all of the constraints. So that's one example of a constraint satisfaction problem. Another example is three-line. And again, I'm going to formulate it using a predicate. So now the predicate again takes 3 bits as the input and outputs 1 bit. And P of X, Y, Z is 1 if and only if the sum modulo 2 of X, Y, and Z is 0. And with this predicate in mind, an instance of three-line consists of a set of variables x1 to xn and constraints, again of the same form. And when you're given a CSP like that, an interesting problem to ask is, what is the complexity of determining whether a given instance is satisfiable or not? The above example, for three-sat, this problem is NP-hard. This is the well-known Cook-Levin theorem. But for three-line, this is a problem which is in polynomial time. And this is, undergrad linear algebra. If I give you a system of linear equations over a field, you can tell me if it's fully satisfiable or not. So kind of the main thing that I'm trying to get at in this talk in one sentence is what makes three-sat hard and three-line easy? And of course, this is not a well-formulated question. This is kind of what we're going to have to do, but this is the main topic of discussion. And towards that, we're also going to try to develop some general theory about CSPs in general, not only these two. And later on, and this is where our work comes in, I'm going to talk about approximation. So far we're only talking about satisfiability, but you can also generalize the discussion to approximation. So let's state things a bit more generally. So in general, a constraint satisfaction problem is defined by a predicate P. So we think of K Array predicates. K is some constant. You can think about it as 3 or 10 or something like that. And you have some fixed predicate, meaning some map from sigma to the K to 0, 1, where again, K is constant and sigma is some finite alphabet. And given this predicate, an instance of CSPP is composed of a set of variables x1 to xn, and constraints that are P applied to a set of variables is equal to 1. And sometimes you have to allow negations and stuff like that, like in three-sat, but I'm going to ignore this for the moment. So don't worry about that. And as we said, the most basic problem you can ask about an instance of CSP is whether it is satisfiable. In other language, I give you an instance psi of CSPP. I promise to you that it's satisfiable, and I ask you, please find for me a satisfying assignment. How hard is this problem from a complexity point of view? Again, in the worst case. And as we already saw, this problem can be NP-hard, like in three-sat. Here's another problem that I claim is NP-hard. So does anybody see what problem does this predicate encode? So it gets two inputs that are from 0, 1, 2, and it outputs 1 if and only if these two are different.
Free coloring.
Yeah, free coloring, thanks. Yeah, so this encodes the free coloring problem, which is NP hard, so that's good. And we also saw some examples of problems that can be NP. So we already saw the free limb problem, and here is another one. And I'm going to ask you for the name of this problem. So now you get 2 bits and you ask whether they're different or not. Yeah, so it's 2 coloring. Yeah, so we know that 2 coloring is in P and 3 coloring is NP hard. So yeah, these are a few examples. But more generally, can you say when this is NP hard and when is it in P? So this is known by now, but this is a fairly difficult problem. And first of all, is it not trivial? So can the complexity of CSPP be intermediate? So we do know that there are some problems that are not P nor NP hard, assuming of course that P is not equal to NP. So the real question here is excluding the possibility of CSPP being one of these intermediate complexity problems. So what we're really asking here is about dichotomy. So we're asking, I give you any predicate P. Does the complexity of CSPP have to be either P or NP hard? And as I said, there is a classical complexity theory result, Lander's theorem, that tells you that there are such intermediate complexity languages, but the point is that these languages are kind of weird, and we hope that CSPP is not one of them. And towards this end, we have the classical theorem of Schaeffer that says that this is true if your alphabet is Boolean. So any CSP over a Boolean alphabet is either in P or NP hard. And this is a classical result from 78. And it took a while, it took 20 years to conjecture that the same thing holds for any finite alphabet, not only for Boolean alphabet. And this is called the dichotomy conjecture. And there's been a lot of work on the dichotomy conjecture, kind of from 2 views. The algebraic view, where there have been many works, and the analytical view, where there was one work suggesting it, and then not much progress. And this was the set of affairs for quite some time, until the conjecture became a theorem, and this was proved by Zook and Bulatov 5 years ago. And they proved that indeed, for all finite alphabets and for all K, and for all predicates, CSPP is either NP hard or is polynomial term solvable. And that's a great theorem, okay? That's really superb. But what they did, moreover, is actually tell you what is the algorithm. So the algorithm, in case the problem is P, so I'm not going to tell you what it is exactly, in particular because I don't really understand it, is some iterated linear programming plus rounding procedures. So it's something very abstract, very concrete. So there is nothing mysterious going on. So you know what the algorithm is. But the theorem is even better than that. It gives you a precise characterization of when the problem is NP hard and when it is in P. And in one word, the characterization talks about a notion called polymorphisms, and in particular, the existence of non-trivial polymorphisms. And I'm going to tell you next what this polymorphism business is all about, but if there are any questions, now is a good time. So what is a polymorphism? So in 2 words, it is a solution mixer. But to say more than that, I'm going to need a picture. So suppose we have some constraint, some predicate P applied on K variables is equal to 1, and we have a bunch of solutions to it. And I'm going to think about these solutions as the rows of some matrix. So in this matrix, I have 100 rows corresponding to 100 solutions, and each column corresponds to a variable. And then on the 1, 1 entry, it tells me what is the value of x1 in solution 1, in the entry 1, 2, it tells me what is the value of x2, and so on and so forth. So I have this table, each one of the rows is a solution. And now what I want to do is take some function that is going to be applied on the columns, and apply it. And if I do that, I get yet another vector of length k with values from sigma. I'm going to say that F is a polymorphism if whenever I do this experiment, meaning take a table consisting of solutions to the constraints, apply F and get a new vector, then this new vector is always also a solution to the constraint. So that's what polymorphism is about. Now, of course, there are trivial polymorphisms. So for example, the function f could always output the first coordinate. And then the result will always be the first row of the matrix, which we know by design is a solution. So this is cheating. This is called trivial polymorphisms, or as I like to call it, dictatorships. And soon enough, it's going to be clear why dictatorships, because you only look at the first coordinate, the rest don't matter. And we don't count these. So the structure is really about the existence of non-trivial polymorphisms. So this is the main creature that one wants to talk about in dichotomy.
It's okay.
Not said anything.
Okay.
That's okay. I don't think we did say anything.
I can't really hear you, so.
Can you hear me now?
Yeah.
Okay, I think there was no comment. No one had a comment.
Okay, thanks. Anyway, so this is very abstract. So let's see an example of polymorphism. So here is a predicate. This is the predicate corresponding to 2SAT. We know that 2SAT is in P. And if you believe me about this theorem, or if you believe the people who proved it, then really the reason that 2SAT is in P is because there exists some non-trivial polymorphism. So let's try to see that, just to be convinced. So suppose I have this table consisting of solutions to this predicate, meaning on each one of these rows I have at least one single one. And now I want to apply some column function and get a new solution. Then what I can do is apply the majority function. Namely, I'm going to take a function that takes m bits as inputs and output 1 if and only if at least m over the 2 of the bits are 1. And I claim that I always get a new solution to P. And why is that? Well, I know that in each one of the rows I have at least a single one. This means that overall in the table I have at least m ones. So therefore, either on column 1 or column 2 or both, I have at least m over 2 ones. So I will get a solution. And here is the claim more precisely. If each row satisfies P, then also the F applied on the column satisfies P. So really, this is kind of a very convoluted way to see that 2SAT is in P, but this is really what's going on. So this is all very nice. This is all about exactly solving CSPs, but I like approximation problems. So how do you put any approximation on top of it? And now I'm going to formulate what we call the approximation dichotomy conjecture. Now this is really a conjecture. It's not something that we know how to prove. And it's going to look kind of similar to other things that we are going to see, but I'm going to try to highlight what are the main differences. So here is a conjecture. I have a finite alphabet, and I have a finite k. And I also have a predicate P such that CSPP is NP-hard. Now, what I want to say is there exists some approximation threshold alpha such that I can approximate CSPP within factor alpha, but doing anything better than it is NP-hard. But I need to be a little more precise. So what is the problem? I give you an instance of CSPP, and I promise to you that it's fully satisfiable. I want you to say, okay, there is an algorithm achieving at least alpha fraction of the constraints of CSPP, but doing more than that is NP-hard. And I'm willing to compromise for not NP-hard, but some hardness under stronger complexity assumptions. But this is the kind of dichotomy theorem you would like to prove for approximation problems. And just as before, you would like also to say what is the algorithm that achieves this alpha approximation. So does it have to be a linear program as before, maybe a semi-definite program, maybe some mixture of both, we don't know. And I already said this is open, we don't know how to prove it, and we think that it's going to take a while. So the dichotomy conjecture took a while to solve, and there is yet another very related result called Raghavendra theorem that also took a while to solve. It's something very similar that we're going to soon discuss. So this is not something that I think will be solved anytime soon, but I sort of view it as a guiding problem that along the way leads to very interesting things. So I hope that towards the end of the talk, I'm going to be able to convince you of that, but for now, this is a conjecture. So what I'm going to do is tell you a little bit about some recent progress towards this conjecture and some related problems that were solved also. So to get to this problem, I'm going to tell you about something very related, but yet very simple, but very different, which is kind of the same problem, except that you drop the fully satisfiable instance requirement. And instead of that, you talk about almost satisfiable instances. And now it's no longer a conjecture. This is now a theorem. It's a theorem of Raghavendra. So it makes the following assertion. As before, fix alphabet, fix k, and fix a predicate. Now it tells you that for every epsilon, there exists some approximation threshold alpha, such that if I give you an instance of CSPP, which is maybe not satisfiable, but it's almost satisfiable, it's at least one epsilon satisfiable, then you can achieve an alpha approximation of it. Namely, you can satisfy at least alpha fraction of the constraints, but beating it is NP hard. And you see that there is an NP hard with an asterisk. This is because it's not really NP hard, it's NP hard under the unique games conjecture, but I don't want to talk about it right now, so you can ignore this asterisk. But anyway, this is really the same as the conjecture that I stated previously, except for this, tiny difference that instead of promising fully satisfiable instance, I only promise 1 minus epsilon satisfiable instance. This is still a great theorem. And in fact, just like in the dichotomy theorem, not only does Raghavendra tell you that this is true, but it also tells you what is the algorithm. And in this case, the algorithm is a semi-definite program relaxation of the natural integer program that you can write for CSPP. And you need some appropriate rounding scheme, which is some rounding scheme based on Gaussian space. So, it fully solves the problem. It tells you how this approximation may be achieved. So at this point in the talk, you may wonder, okay, why is this guy talking to us about satisfiable, almost satisfiable? What is this little epsilon? Why do we care about it? And what I'm going to argue is that this little epsilon may seem at first negligible, but this is really, for some problems, it's make or break. So there are some problems where satisfiable versus almost satisfiable makes a big difference. So for 3-line, for example, if I give you a 3-line instance and I promise to you that it's satisfiable, then you can solve it completely. Then there is no issue. But if I only promise to you that it's 99% satisfiable, then you are in bad shape. Then you cannot beat half. This is a classical result of half study. So you see this little bit of difference between satisfiable and almost satisfiable makes a lot of difference for some problems. But of course, for some other problems, it doesn't make any difference. Like 3-sat, it still is harder. And kind of the question that we're trying to get it is, for what problems does this satisfiable versus almost satisfiable make any difference? So this is really an interesting problem from this point of view. And for the sake of concreteness and for the rest of the talk, I'm going to focus on the 3-array case. I'm going to talk about k equals 3, but much of what I say can be generalized beyond it. So with all of this in mind, I can tell you what is our guess as to when is there a difference between satisfiable and non-satisfiable instances. And in 2 words, our guess is there can only be a difference if the predicate you are looking at has an abelian structure. And now we're going to try to formalize what does it mean to have a abelian structure. But really the intuition is, well, if really, it's some linear equation over a finite field. Linear equations is easy. And if your predicate is not some linear equation, then too bad. Then there is no difference. But of course, what does it mean to be a linear equation? It's not clear, so we need to formalize it. And here is one way to do it. So suppose we have a predicate P from sigma to the 3 to 0, 1. We say that P can be linearly embedded if there is some abelian group, G, with an operation plus, and 3 maps from sigma to G that, are not trivial. They are not all the constant 0 function. And these maps say that if you take anything that evaluates to 1 in P, apply these maps on X, Y, and Z, and add up, then you get a 0. Informally, in a little bit of different words, we say, if you relabel sigma by some group elements, then the support of a predicate is contained in a linear equation. So let's think that sigma itself is a group, and all of these maps are the identities. Then this really means that anything that satisfies P satisfies some linear equation. But of course, you need to take this labeling into account because the group is not going to be told to do outright. That would be too good to be true. So this is the informal description that I just mentioned. And here is the moral conjecture. And when I say moral, I mean, this is false, completely false. But we believe that something close in spirit should be true. So the conjecture, or the moral conjecture, says that if you have a predicate, and this predicate does not have any linear embeddings, meaning it's not contained in any linear equation, then the approximation dichotomy conjecture should be true for CSPP. And on top of that, STPs, meaning semi-definite programs, should still be the best algorithms possible for this. So again, the high-level message here is, if there are no linear structure, then still SDP is the best. Still, you cannot do anything better than. And so we started working on this project, a while back, but for the majority of it, we didn't get anywhere. Until finally, we managed to prove that this moral conjecture is true for some predicates. So we managed to prove that for some class of predicates, this is true. But as I'm going to tell you about, there was some more recent progress about it. And in particular, I'm going to mention it a bit later. So kind of recently, we managed to prove that actually this moral conjecture is true for all predicates on K equals 3. And actually, along the way, we saw some relations to some other problems, namely direct product testing and also some multiplayer power repetition theorems. So I'm going to mention that in the end, but I think that there should be some interesting connections all over the place. So taking a step back, let me tell you about the components that go into these proofs of these complexity results. So, whenever you want to prove such result as this moral conjecture, you need to have a hardness result. And hardness result, you do a hardness result, meaning you do a reduction, and a reduction has to start somewhere. So you need some starting problem. For the dichotomy theorem, you can take any NP-hard problem. You don't need anything specific. For Raghavendra, you already need something more heavy. You need the unique gaps conjecture. So this is some problem that we suspect is NP-hard, but we don't know that, so we conjecture it. And because this approximation dichotomy conjecture sort of combines the strengths of both of these theorems, you are going to need at least something as strong as UGC. And we don't know that, of course, everything is speculative here, but there is a recent conjecture called the rich 2-to-1 games conjecture, which we believe should play the role of UGC in this business. So the benefit is that you have hardness of satisfiable instances in this problem, but it's harder to work with. So the second component of all of these results is some error correcting result. So error correction arises when you want to talk about approximation problems. So for the dichotomy theorem, it's not needed. For Raghavendra, you need what is called the long code over product domains. And for us, again, it's speculative. So I'm going to speculate that what you need is multi-slices. So this is some analog of long codes, which is more compatible with this rich 2-to-1 games business. And finally, you really need the meat in all of these constructions, which is some analytical tools. In the dichotomy business, this is what we refer to as polymorphisms, and we saw earlier. In Raghavendra theorem, it's something called dictatorship tests. And very creatively, in this approximation dichotomy conjecture, we believe that you're going to need something more general, and I'm going to call it a generalized dictatorship tests. So these are the components that go into these results. And next, I'm going to try to tell you a little bit about what is this dictatorship business. And actually, I'm going to try to convince you that dictatorship tests are really the same as polymorphisms, except that you try to maximize something different. So kind of this picture, all collapses into itself, but it's all very nice in my opinion. So in the rest of the talk, I'm going to tell you a little bit about what is dictatorship tests, what are the challenges that we face, and a little bit about why I think that this may be relevant to other problems. So what is the dictatorship test? Well, let's recall the setting of polymorphisms. So we have some predicate P, and we have a table of solutions. So each one of these rows is a solution to the constraints defined by the predicate. And what is a polymorphism? Well, we said that it's a function that we apply on the columns, but now I'm going to change it a little bit. Now I'm going to allow you to use a different function for each column. So it doesn't make a huge difference, but let's think about that. So I'm going to apply the function f on the first column, the function g on the second column, the function h on the third column. I'm going to get fx, gy, hz. This is a new vector of length 3 in sigma to the 3. And we said that this is a polymorphism if whenever I do this table and apply f, g, and h, I get a new solution to the predicate. So this is what a polymorphism is, and recall that we had this discussion about non-trivial polymorphisms, meaning we don't want you to simply pick one of the rows. This is not considered a proper polymorphism. So what is a dictatorship test? Well, in dictatorship test, you're going to have a stronger assumption than non-triviality. So instead of just assuming that each one of FGH is not a dictator, meaning it's not just the first element, you're going to assume that each one of them is far from being one of these trivial functions. Each one of FGH is far from being a dictator. So I give you a stronger promise, but now I want something stronger in return. So I want the experiment to yield a solution to P with as high probability as possible. So what is the probability over here? Yeah, okay. So I didn't specify that. But in any case, so the probability here, so you can think of this matrix drawn randomly, meaning each one of the rows is sampled from some distribution over satisfying assignments of P. So this defines the distribution over the matrix. And then the probability that I want to maximize over here is I sample X, Y, Z as above, and I want Fx, Gy, Hz to be a satisfying assignment for P with as high probability as possible. So I hope that this is convincing that polymorphisms and dictatorship tests are really the same, except that you ask for some slightly different quantity. Instead of always you want as high probability. But this is what is most relevant for approximation. And with respect to this, there are two quantities of interest. So you can define the parameter beta, which is simply, take all of the possible functions f, g, and h that are far from being trivial. And just choose the best ones. Just choose the ones that maximize this probability. this is going to be referred to as beta of P. And you can also define alpha of P, which is kind of the same quantity, except that you limit the class of functions FGH that you're allowed to apply. Instead of just applying any functions that are far from being trivial, I only allow you to use low degree functions. And I don't want to define low degreeness here formally. You can sort of imagine what it means. It's really the same as low degree in terms of monomials. So the interesting thing is, it turns out that beta of P is an upper bound on the best algorithm you can achieve. Because you can show that any algorithm can be used to construct FGH that achieve some nice probability in this game. And very interesting also, it turns out that this alpha of P is an algorithmic lower bound. Namely, if you have FGH that are low degree functions and achieve some probability, then you can actually design some Gaussian rounding scheme based on FG and H and get roughly alpha of P approximation for P. So just by definition, it's clear that always alpha is smaller than beta. And this makes sense because, beta is an upper bound on the best you can do and alpha is a lower bound. And what turns out to be the case is that if you look at almost satisfiable instances, then actually alpha and beta are the same, absolute law of one. So this is not trivial to see, but this is true. And this is what tells you that whatever you can do with any FG and H, you can do with low degree functions. So therefore the upper bound and lower bound coincide, and you get this dichotomy behavior at alpha of P. And this in particular means that STB is the best you can do. So that's all nice. That's all applicable to almost satisfiable instances. What about satisfiable? So to talk about satisfiable instances, I'm going to try to elaborate a little bit on what's going on between this alpha and beta in almost satisfiable instances, and tell you a little bit of how this is proved, very little. So here is a related analytical question, which is sort of the heart of the matter when you want to prove that alpha and beta are the same for almost satisfiable instances. So you have your predicate, and you have some distribution over satisfying assignment. And now we want to prove that, low degree functions do the same as high degree functions, the same as general functions. So if you think about it for a little bit, this really means that high degree functions cannot achieve anything. And this is really the statement that we're trying to prove now. So now we have FGH that are all high degree functions. And we want to show that they cannot contribute anything. And what turns out to be of interest is, what is the correlation that you can achieve between fx, gy, and hz when you draw again xyz from this table according to the distribution mu? So what does it mean correlated? Well, I just mean take the product of these three functions. Can the expectation of them be bounded away from zero? And in the almost satisfiable case, you can actually ensure that this distribution mu is rich enough so that there can be no such correlations. And in one word, the reason that this works is that, so and now I'm going to say this formidable word, tensors. So, this XYZ is really a tensor, right? It's a three-dimensional tensor. One axis is X, one is Y, and one is Z. And it turns out that when you look at sufficiently rich distribution mu, you can actually forget about this being a tensor. You can flatten it into a matrix by, merging two symbols X, Y, and Z. And then this becomes a matrix problem, matrices we know and like. And luckily enough, you can arrange these matrices eigenvalues which are less than one, and all is good. This is kind of the way this is proved. So, so in one word, use flattenings, and then it's sort of easy. So what about the satisfiable case? Well, so first of all, the question is, can this be correlated? And it turns out that you can actually not do the same proof as before, because you cannot arrange that flattenings work. So we're kind of stuck. And actually, the statement is even false if you have linear embeddings. So suppose my predicate P has some linear embeddings, and let's say for concreteness, That's it. It's a linear embedding into F2, addition modulo 2. I claim that now I can show you high degree functions that are highly correlated. And this is very simple. So I can just define fx to be -1 to the parity of what the x's are mapped to under sigma, gy to be -1 to the parity of what the y's are mapped to under gamma, and h to be -1 to the parity of what the z's are mapped to by a phi. And you can just check by the definition of embeddings that when you multiply out f, g, and h, you just get 1 always, because sigma of x1 plus gamma of y1 plus phi of z1 is always 0. The same holds all coordinates. So not only do you get correlation, but it's perfect correlation. So things are a bit tricky when you look at the satisfiable case. And when you have linear embeddings, this is even false. And our analytical conjecture says that actually, this is the only way this thing can be false. Namely, if you don't have linear embeddings, then there are no functions f, g, and h as before that high degree, and yet their values are correlated. And as I said, we prove this hypothesis for the case that k equals 3. The case that k is larger, so I don't want to state it, but we believe that it's much harder. I'm going to say a few words about it in a moment. But even this is fairly difficult, and along the way, we realize that you can use this sort of lens to apply for different problems. So let me tell you in 2 words about the techniques. So I already said, flattenings do not work. And this is similar to the case where you have some tensor, which is kind of hard. This is at least what you suspect. But when you flatten it into a matrix, nothing interesting happens. This is what happens for us. We have some tensor that we believe is hard, but once you flatten it into a matrix, angle values become 1, and we cannot say anything. And this jump in difficulty arises in multiple problems. So we all know that tensor rank is hard to study. Multiplayer communication, but it's certainly hard. There is this thing called the Gowers norm that becomes very, very hard when you go high enough. You need some heavy guns. And I believe that we heard on Monday about multiplayer power repetition, and this also becomes harder in 3-player games. And in fact, we don't really know much about it. So, there is this jump in difficulty from 2 to 3, not only from 2 sat to 3 sat, but, also from these problems that we study. So I told you that many things don't work and that it's very hard in a bunch of different problems. So what we do, well, in an earlier paper, what we managed to do is reduce the problem to some problem in non-abelian Fourier analysis. So we kind of show that for some class of predicates, you can actually show that such predicates are really non-linear equations of non-abelian groups in disguise, which is kind of the intuition in this business. But this is only for a special class of predicates. And to apply for general Fourier predicates, we actually had to go for some kind of weird inductive argument that the only thing that I can say about it is that I think that it works. But basically, this inductive argument says that the fact that you don't have any linear embedding corresponds to some base case, meaning that for one variate function, you cannot achieve perfect correlation of 1. And then for n variate function, you need to do some tensorization argument that says that this correlation decays with n. And I think that it's true, and I think that it works, but it's non-trivial. Let's put it that way. So this is what we do, and this is kind of one of the main things that I think about nowadays. But I think that this embedding philosophy, meaning trying to ask when are the solution to some problem can only be achieved by linear embeddings, is some philosophy that may be useful in a bunch of other places. So of course, the top question that remains open is whether this analytical hypothesis remains true for all Ks, not only for K equals 3. And then beyond that, what if there are linear embeddings? What do we do then? Can you say that this is the only way you can achieve correlation? And secondly, the question is, can you use this sort of thing for other problems, not only for analytical purposes in PCP? And I believe that it should be usable for other stuff. And by now we have some evidence for it. So we had some recent works showing some progress about some related problems using this kind of lens. So in particular, we managed to analyze what is called the linearity testing problem over the p-bias distribution. And actually for that, we needed to prove some improved direct product theorem. So I can tell you the statements, but I didn't want to have too many quantifiers on the slide. And finally, very recently, this end of last week, we managed to show that you can use this sort of lens to prove exponential decay parallel partition theorems for the GHZ game. So the GHZ game is one of these 3-player games that is kind of difficult to study with information theory techniques. And it was sort of, I guess, the stepping stone for recent results about parallel partition theorems on 3-player games. And again, using this, you can show that the value is actually exponentially decaying and not only polynomially, as was previously known. And, you know, in general, the problem that I would be most interested to see solve this approximation dichotomy conjecture. But I think that this is, you know, a long-term goal. And I believe that along the way, there will be many interesting things to be discovered, just like I mentioned previously. So I believe that this will impact other fields. So that's all I have to say. Thank you.
Okay, thank you very much. Are there any questions? I have a question regarding your GHZ games. Could you tell us the statement? So the exact statement of because we had a nice talk on this parallel partition on the GHZ games. It would be nice to know now, how's your decay?
Yeah, it's so there exists an absolute constant epsilon greater than 0, such that the value of the GHZ game repeated n times is most 2 to the minus epsilon n.
Like you have bounds on epsilon?
Sorry? Yeah. So actually, so the paper is so short and so simple that we actually computed the bound. And I think that this epsilon was like 1/1028 or something.
So you don't get anything for small values. It kind of like kicks in when the values get large.
Yeah. Yeah. So yeah, but this is very typical to parallel partition theorems. I think that even for 2-player games, this is the best that we know how to say.
Are there any other questions? Maybe by the remote audience? I suggest that we thank our speaker again.